All right, so let's take a look at the basic rocket problem. Now, these can get nuanced at some point, but I just don't want to get too into the nuances in this particular video. So I'm just going to start out with I have a rocket, I have fuel, and I have an environment. So the rocket is going through the environment, and we're going to, of course, start out with no air resistance. Well, actually, we'll stay with no air resistance. We're going to start out with no gravitational pull on the rocket to start with, and then we'll add gravitational pull, and then we can add air resistance in a separate video. But I'm going to use R, F, and E as representatives of those objects. So I'm going to let M be the mass of the rocket and the fuel at a moment in time. Now, some derivations of this will separate. They'll have mass of the rocket and they'll have mass of the fuel as different entities. I'm going to keep them combined in my derivation. We end up in the same place. So dm is a change in the mass of the rocket. It would be a negative number because as the rocket burns fuel, the rocket does get less massive. And therefore, since that is the change in mass of the rocket, well, since that's coming from change in fuel, we have a negative dm here. That's the mass of the fuel expelled. I'm going to let v sub re be the velocity of the rocket with respect to the environment. This is common notation here with the double subscript. So that's what has that velocity in that with what it is in relation. Now, the vector notation becomes a nuisance, so I'm just going to drop the vector notation for the sake of writing. All the v's are velocities and not speeds. So that. Now, if we are looking at the velocity of the fuel with respect to the environment, that would be the velocity of the fuel with respect to the rocket plus the velocity of the rocket with respect to the fuel. This process right here is Galilean relativity, and I believe there's a separate video on that somewhere. V sub fr is ultimately what we're going to be using in our final formula here. That's the velocity of the fuel with respect to the rocket. So generally consider the exhaust velocity. There are a lot of sites that I have been to where they don't define it properly, and I just want you to realize that the exhaust velocity is the velocity of the fuel with respect to the rocket. So if the velocity of the rocket is in the positive direction, then VFR is in the negative direction. So rocket, fuel. So if the rocket's traveling in the positive direction, then the fuel is traveling in the negative direction. That's what this bit down here is saying. I want to take a look at the momentum of the system, which is the momentum of the rocket with respect to the environment plus the momentum of the fuel with respect to the environment. So this would be the momentum of the system with respect to the environment. So the initial momentum is just I have rocket and fuel going at a certain velocity. Then the rocket expels fuel, so there's a change in mass here. Again, this is going to be a negative number. This is the rocket here. Rocket and remaining fuel. And this is the part of the fuel, momentum of the fuel. It's the mass of the fuel times the velocity of the fuel. We have velocity of the rocket plus this change in velocity of the rocket, all with respect to the environment, space, planet, whatever it happens to be. If I go ahead and FOIL this, I end up with that bit right there. This is a result of these two binomials being multiplied together, and you can work it out. First, outer, inner, last. And then that is just you're multiplying two numbers together. I removed the parentheses and stuck the dm at the end. Now these are the same, so they cancel out. This dm here, this is the change in fuel. If you're not familiar with the calculus notation of it, this is, again, is just the change in fuel. And this is the amount of fuel change. This is the change in the velocity. We're dealing with really tiny changes here, and so this is practically zero. So that term is going to go away. So what I'm left with is this term, that term, that term, and that term. But recognize the velocity of the fuel with respect to the environment, as we have over here, is the velocity of the fuel with respect to the rocket, plus the velocity of the rocket with respect to the fuel. And so I make that substitution in there, and that expands to this. So VFR plus VRF times dm. These two terms cancel out, and what I'm left with is just this term and that term. If I add this to the other side, and then by the reflexive property of equality, flip it around, I get mass of times the change in the velocity of the rocket with respect to the environment is equal to the velocity of the fuel with respect to the rocket times the change in mass. Well, multiplying times the change in time, I get mass times the change in velocity over change in time is equal to the velocity of the fuel with respect to the rocket times the change in mass over the change in time. Now, the change in velocity over change in time, that's the acceleration of the rocket with respect to the environment. This is mass times acceleration. And this over here is known as thrust. This particular factor right here, dm dt, is known as the burn rate. Now recognize that this is a negative number because this is the change in mass of the rocket, and the rocket is losing fuel, and therefore the change in mass is a negative number. VFR is negative, as outlined before. If the rocket is going in the positive direction, the fuel is going in the negative direction with respect to the rocket. And so we end up with this velocity of the fuel with respect to the rocket times dm dt, or change in mass over change in time. So this is known as the thrust. We can treat it like a force, at least. Now this is when you start getting into some of the nuances. Some sites and sources seem to feel that thrust is the total force acting on the rocket, and other sources will treat thrust as just this part of it. So in the case of a rocket with no gravitational field, nothing else around, there's no difference in those problems. When you bring the Earth into it, now comes the question of, does the thrust include the weight, or is it the thrust minus the weight typically? I guess the rocket could be heading towards the Earth, in which case it would be thrust plus the weight. Let's just do a simple example. 2,000 kilogram rocket, 500 kilograms of fuel takes off. This is actually a very small amount of fuel for a rocket, but we'll get into realism in a moment. I have it launching from a space dock, so I want to make g as close to 0 as possible. Little g, 0 meters per second squared. The speed of the fuel with respect to the rocket is 50 meters per second. And the fuel is burned off at a constant rate of 10 kilograms per second. So this is, what's the initial acceleration? F equals ma. The force is the thrust. And so we have our thrust equation right there is equal to mass times acceleration. Velocity, I gave that number to you. Again, if I assume the rocket goes in the positive direction, as stated right there, the speed is 50 meters per second, but the velocity is negative. 10 kilograms per second is being burned off, and so I end up with force equals mass times acceleration. Now that is the sum of these two, because remember that mass is the rocket plus the fuel. And we end up with an acceleration of 0.2 meters per second squared. So looking at the second problem, we're now going to take off from Earth, and of course no air resistance. Again, much smaller than, let's say this were a space rocket trying to get something into outer space. For instance, for the shuttle, fuel is about 85% of the total initial mass. We'll get into realism later on. What's the rate of fuel consumption necessary to take off? Let's assume that the velocity of the fuel with respect to the rocket is negative 500 meters per second. So force diagram, I got thrust going up and weight coming down. Assume up is positive. Thrust minus the weight is mass times acceleration. And then looking for the point at which acceleration is greater than 0, in other words, the point at which the thrust is greater than the weight. So I'm looking for, this is my thrust equation. That's my weight, because I'm still close to the surface of the Earth. And so just solving for my burn rate, the rate of fuel consumption is the weight divided by that velocity right there. And so I have my total mass, again, fuel and rocket both being launched, times 9.8 meters per second squared, because it's Earth, divided by the negative 500. And so I get negative 588 kilograms per second. That is the rate at which it needs to be burned. Sort of expanding on this, if we look at the equation from this right here, and I'm going to go ahead and, starting from that, I'm going to get the velocities on one side and the mass on the other. So we get this. Doing a little calculus, we integrate both sides, and ultimately we end up with, well, that is relatively constant. We're considering that constant, and so the velocity of the fuel with respect to the rocket is not related to the velocity of the rocket with respect to the Earth. Well, okay. These are independent of each other. And so therefore I can factor that out and integrate just the velocity of the rocket with respect to the environment. And ultimately end up with a change in the velocity of the rocket. So this is the rocket with respect to the environment, divided by the velocity of the fuel with respect to the rocket is the natural log of mass over m sub naught. This is the total mass that we start with. That's rocket and fuel, the way I've set it up. And this is the mass at some later time. Solving for delta V, we can find the change in velocity to be velocity of the fuel with respect to the rocket times the natural log of the mass at some moment in time later, divided by the initial mass. Recognize that's a negative number. That's a negative number because this numerator is less than the denominator. This is known as the, I'm not going to begin to try to pronounce that, but it's his rocket equation, and it is the classic ideal rocket equation. And so one last problem here. So if I'm using a rocket from problem 1, what's the maximum speed? Using that equation we just derived, we have negative 50 meters per second times the natural log of the mass of the rocket divided by the total initial mass. And again, I can use mass of the rocket because this is the maximum speed. And I am assuming that the burn rate is constant throughout all that. And we ultimately end up with 11.157 meters per second, which is about 25 miles an hour. So, and the last little bit of realistic numbers. These are numbers I've pulled off the internet. So this is the percent of the initial mass that is fuel, and so the rocket mass, that's space shuttle specifically, found a lot of information on the space shuttle. And burn rates, and a lot of it's sort of scribbled down here, but the burn rate is about negative 5,000 kilograms per second to start out with. And we get a total thrust of 2.3 million newtons. And so that's just some of the statistics that are involved there. And I'm going to flash this next one up. This is some of the other information that I have pulled together. Obviously, it's in still a crude form, but we end up with some other burn rates of, that's the actual velocity of the fuel with respect to the rocket. That's actually the speed. I don't have the signs in there. So a little over 2,300 meters a second. And then after, that's for the solid rocket boosters. And then after those fall away and you're left with the space shuttle main engine, the exhaust speed is greater. But then again, you've got 3 main engines, whereas you've got 2 rocket boosters. That's part of it. And there's some other factors involved. But there's just some of the stats. And it might make its way into an actual problem.